All right. So, and also due to that severe low temperature day, we canceled a class. But very luckily, that class that we canceled is the most kind of classical and almost like a review type of class that you can find materials in almost all the previous machine learning classes. So I encourage you to read the materials yourself, which basically just give you the foundation of how to do density estimations and how to do single graphical model estimations when all the nodes are observed and when the graphical models are directed. So maybe just to put that back into the context, this is now the landscape of learning graphical models. We touched upon a little bit about the inference already. That's actually one of the major reasons we use graphical models, because you want to use a model to answer questions. But now where the model come from, and here are the scenarios, right? We already become aware about completely observed directed graphical models. And we also worked on partially or unobserved graphic models directed. Anybody want to remind me what is the killer application algorithm for these type of questions? Partially observed or unobserved directed graphic models. What algorithm you use? EM algorithm, right? Basically, the idea is that, again, so from this graphic model class, the least I want you to get out of it is to remember, say, a list of 20 or 30 algorithms. It's to develop a rationale and a taste about tying together a lot of stories and look at the inner beauty and the connection between them. Why we start with a fully observed graphic model? Because everything basically is observed, it factorized into local estimates, and then you just count, or you just do local frequency computation. And then when something become unobserved, you do inference and make them as if they're observed. And then you can plug in to those partially observed graphic models to turn them into an observed graphic model problem. So that's the rationale behind it. Of course, these are heuristic. Usually good ideas often begin with a heuristic. It just worked. But better researchers are not going to stop just at the algorithm that worked. They actually want to dig out the foundations behind that. And that's why graphical model and multivariate statistical machine learning becomes a thriving field, because people not only want to get things work, but also need to understand why it works. That's why we have this, in fact, not very simple theory behind the EM algorithm, which is what? It is what? It is a coordinate descent algorithm, right? You are descending in one dimension, a approximating distribution Q, and you want to find the best Q out of it. And then on the other direction, you fix that Q, and you find the best parameters of that distribution, and you alternate, right? So you can see this old school, but very elegant taste and style of a study is often missing nowadays in machine learning research. People just worry about getting things work, and then move on to another problem and use the same hammer to basically work on other problems. Then you hit a winter, because at the end of the day, maybe when people ask for explanation, ask for repeatability, and ask for robustness, you have no way to further those fields. So that's why I think it's interesting to go beyond just remembering the algorithm. And I'm trying hard to, again, give you not just the algorithm, but also the inner rationale behind it. Today, actually, is a particularly interesting lecture, because there are some non-trivial mathematics I'm going to present to you. And also you can see why it is a useful thing. And also, graphic model is a highly modular thing. That means that there are many, many components that you can replace with different choices. For example, the estimation principle itself. Right now, because the class is known as a probabilistic graphic model, therefore you use a maximum likelihood or sometimes a Bayesian estimation to drive the estimation. But you could just treat it as graphic model and move that word probabilistic away, and then it becomes a generic loss minimization problem. You can introduce other things like max margin, max entropy, and all different things, as long as their cost function can be designed and compiled by cleverly pulling together local structures. Okay, and again, graph become a guideline, for you to achieve that effect. So we're going to see those examples later. So just look back to the MLE for Bayesian networks. The single most important thing that you want to work with home is this one, right? However large the graphic model is, at the end of the day, you need to care something like this, which is due to the factorizability of the graphical model. Now we ask, is this trick going to apply to undirected graphic model? That's the question that become very interesting, because sometimes heuristic and intuition just can fool you. For example, in here, we have a undirected graph model, and we know that using the Hammerschlag-Lipper theorem, we can define a undirected graph model using, this Gibbs distribution, right? And there is a very mysterious z, which is known as partition function. That is basically the sum or the normalization constant of those product of unnormalized potentials. Okay, now. Just by looking at this equation, I guess you already see something troublesome. Suppose that this phi, the potentials, contain some hidden parameters. Okay, it's basically something you use to describe the strengths of configurations in this clique and so forth. And you want to learn those. And I told you already that everything is observed. You can literally just plug in your observations into all these functions. Can you compute the parameters within phi easily? Why? Because you don't know this value. Therefore, this whole thing is not quantifiable, right? And when you want to do the MLE style estimation, you need to take derivative of this with respect to the whole thing. And here, there's something that you don't even know. So there isn't a explicit way to optimize against. So that's actually a big issue in undirected graph model. But on the other hand, why we use undirected graph model? Because it's useful. There are some models we know that some phenomena we know that only can be described by a undirected graph models, such as a Ising model, like the image problems that we talked about before. Okay. So let's take a deeper look about what's going on there. So here we have the log likelihood of this is the log likelihood of the likelihood of the undirected graphic model, and let's introduce a few terms, right? We want to introduce a term called clique counts, total counts and clique counts. Counts are basically the basic thing, sufficient statistic, in other words, you want to understand and obtain from data, so that you can make connections or make estimates of the model, right? And the total counts means that the number of times a particular configuration appeared in your data set. And the clique counts is basically the number of times a particular configuration within the clique appeared in the data set. And by definition, they can be obtained by marginalizing over the total counts. Okay? And suppose these two are given, then you can write down your log likelihood, okay, using this. And here I had a little trick, because for simplicity, let's first assume something, say, discrete. Let's just sum over all the x possible configurations. And here I did a slightly, I wouldn't call it a reparameterization, it's just a different expression. Okay, you sum over x. That means that you use a delta function to clamp those values of x that is consistent with your observation of the data, and then count 1 every time you see it. Okay, and that basically makes the connection of the log likelihood into those m's that you obtained directly from data. So this effort is to make the connection of a symbolic expression of the log likelihood over those actual observations you get from data. Okay, And again, we have this nasty z that we need to worry about. Okay, so clear about our problem? Yep.
Can you clarify what's a clique count?
What is what? A clique count. Do you know what is a clique?
Yeah.
Okay. And the number of times, total counts is the number of times configuration of the entire variable sets is observed in the data set. And likewise, clique counts, the subset which is in the clique. Okay, clique configurations of variables in that subset is observed. Okay, so let's do a little bit more. Let's work very slowly. Do you know how this phi might look like in here? When we say parameters, what they are, I just want to make sure that you're still remembering our basis. Rather than, because being symbolic is a habit of mathematician, and we are not mathematician. I want to declare it here. Even though I publish paper in Math Journal, I'm not a mathematician, I'm a computer scientist. I need to make it work. Okay, so therefore, without doing symbolic inferences, and in addition to doing symbolic inferences, I need to actually put those things on computer memory and small numbers. So what are these phis? Remember that? Only when you know this, you actually start to appreciate the size of the phi, the way you parameterize it, and so forth, all matters in your modeling problem. Because to theoreticians, these do not matter. You forgot what is phi already? What is potential function? Now we can review it. All these are too abstract. Let's do physical. Let's do very, very physical. What are you going to put on a piece of paper if I want you to put phi?
Table.
Okay, it's a table of numbers. And they don't have to be normalized. They are probably all positive. Right? So basically, yes, phi of xc is basically just xc and associated with a number. Maybe let's call it alpha and a whole bunch of that. Right? So our goal is to estimate. That's one way. There are actually even fancier way of parameterizing we're going to touch upon later. But how to get those numbers? So obviously, if they're numbers, you probably know that the natural way to do it is to use the old trick of calculus, right? We have a objective function. We are going to take a derivative of this with respect to those numbers which are unknown, and then set the gradient to 0, right? And then I should get a maximum likelihood estimation, right? Okay, there are two terms in here. The first term is rather friendly. You have at the end of the day, this log is taken out to be the denominator. The second term is a little bit irritating. Okay, I'm not going to walk you through all these little algebraic tricks. You may want to know it, so do convince yourself that this is the way it should be. Okay, after you go home. But at the end of the day, we are basically having the derivative of both terms of the log likelihood, and it's interesting to now put them back. Okay, it is look like this. And also, you may want to set them to 0 so that you can hopefully get your estimation of the phi. And then what happened? The phi canceled. The very thing that you want to solve vanishes. Okay, so for some reason, this trick didn't work. This calculus method didn't work. And you get some useful facts. Okay, the useful fact is that if you get the estimation right, so that your eventual P of xc, which is the marginal likelihood on a particular clique and on every clique, is going to satisfy some equality, which is that this equals to this, which we call an empirical distribution. Basically, it's counts by total counts. Okay, some's not surprising, right? We know that in Bayesian network or in mainstream maximum likelihood estimation, the mean parameters or first order moments is equivalent to the sample statistic average, something like that, right? And therefore, you get this fact out of it. But unfortunately, it is not very helpful because this is describing you the marginal probability of the clique. What we want is not the marginal probability of the clique. What we want is the potential function of the clique. Unfortunately, in the undirected graph model, these two things are not the same. Are you still with me? Okay, so I'm trying to be very slow because these are some counterintuitive, well, I wouldn't say counterintuitive, but less intuitive concepts hidden behind the undirected graphic models. All right, so for that purpose, people realize, for that reason, people realize that, some additional serious work needs to be dedicated into undirected graphic models. And in my earlier version of the class, I have a list of multiple dimensions that we want to look into, including examining whether the graph is decomposable, triangulated, and so forth. These concepts, I still think they are insightful and very, very interesting. But again, the field is evolving. Very, very few solutions and the technologies nowadays are using this technology. So I'm going to skip that. If you are interested, you can go back to Jordan's book or Daphne Kohler's book and get a historical account of that. I'm going to now give you two most insightful and useful workhorse algorithms. Each of them solves a particularly popular and important class of MRFs. And again, the algorithm themselves, okay, is important, but it's not just really the key. The key is that you can see how the differences, okay, in this two scope of the problem can cause such a big differences in the algorithmic approach. And also, you can appreciate how little algebraic tricks, can sometimes, give you a great kind of advantage, in relaxing the problem from a very complex to easier ones. Okay, so the first algorithm is called iterative proportional fitting. And also, by the way, I have to share with you my personal taste here. I like the way older school algorithms are named. It's boring, iterative proportional fitting, and generalized iterative scaling. By reading the word, you actually know exactly what algorithm is doing. Okay, it's very different from nowadays approaches. People are using the consequence of the model or maybe the desired consequence of the model to name a method, such as deep learning. Okay, so because you don't actually know what's going on in the whole thing, therefore you have to have many different versions of interpretation depending on how you use it. But here, these two algorithms actually are very, very clever and mathematically also intuitive just by looking at the names. The first method is targeted for MRFs with the tabular potential, the one I just mentioned. Okay, you have numbers behind every configuration. And the second one is for what we call the feature-based potentials. And I'm going to tell you what those models are. It's very, very interesting. And at the end of the day, if I have time, and I still have my voice, I'm going to maybe share with you some interesting stories on the art of model design, which happened actually a while ago at CMU, using one of these models. Okay, so iterative proportional fitting, IPF. So back to this equation, this identity is kind of an anticlimax, right? So it gave us a identity that is factual, but not very useful. Now, in the future, you will have the opportunity to discover many such equalities in your occasional or unpurposed proofs. That actually happened to me a lot. Sometimes my proof all went through and all the algebra appeared to be very beautiful and fluid, and at some point I reached to identity. Okay, showstopper. I cannot go further because I lost my variable. Or I just find a trivial effect. So how to recover from that, right? So in here, I found it's very interesting. It's a very simple idea. Even maybe a high school student could maybe figure out, depending on where he studied high school. So this one is a identity function, and what we want to study, what we want to estimate in this particular equation, and what is the result of the estimated results, right? So obviously, these two things, the phi's, are something we want to estimate because they contain open space parameters. Once you know the phi, you are able to derive this, right? Compute all the marginals because you know the distribution already. And this guy, of course, is a given fact because you can count them from data. It is the empirical marginal. Okay. How about we start to break the symmetry from both sides and make the two things different? For example, here I have two appearances of something we want to estimate. How about we make this equation now, the old trick of fixed point iteration, right? I'm going to basically introduce a time step here. I call this maybe an older version. I call this a newer version. Okay? And that basically turned this identity equation into a fixed point equation. And by rearranging something, I actually got this. I'm going to now have I end up with an update function where the next, suppose I start from somewhere, and my next estimation of the same quantity is going to be equivalent to the previous version multiplied by this identity. And what is this? It's also very interesting. It is a proportion of your empirical marginal that you can count from data over the current version of your estimated marginal based on your model, okay, which should be derivable from this number. So that's why we say that in undirected graphical model, even if you observe the data already, you still need to do inference. Here you are doing now inference over XC as if they are not observed. Okay, remember in EM we do this all the time, right? In EM we basically need to estimate whatever that is not observed using the current estimation of the parameters. Okay, and here the story gets a little bit further. You do estimation of or do inference on even observed random variables given the current model when you want to do the corresponding estimation of sufficient statistics or parameters. Okay, so that's it. Actually, this is just the algorithm itself. It's called the iterative proportional rating. And then this is a fixed point heuristic. Does it converge? What it is doing, right? There are some additional questions you need to ask before you, I guess, getting to this point and writing a paper. It may be okay 30 years ago, but now I think it's not going to be working. You need to say a few more words. So here are some more stories behind it, but still very, very simple, right? You can find that, first of all, once you estimate this, the next thing you can do is to, change another clique and, do this over every other clique. Because when you compute this, do you need only one clique function or all clique functions or clique potentials? You need to have all clique potentials, right, of whatever current version you have in your computer. Therefore, it is actually a fixed point program, not only over time, but also rotating over all the potential functions. Okay, and in fact, you can prove, as I'm going to show you an idea in the next page, that this is, again, a coordinate ascent algorithm where you are attaining the optima, okay, in every direction when you hold the other direction fixed. And you are only going to improve that. Therefore, as long as the loss function is convex, you are going to converge. And if it is not, then it is going to converge local optimum, just like EM algorithm. So at least that provides you a a justification that this algorithm is not doing random work. Okay, it is going to converge you somewhere. And this technique sometimes is also known as eye projection. Okay, what this guy is doing is essentially to project a distribution, from one space to another space where only one potential is allowed to change. Okay, you can imagine that there is a space of distributions where, potentials are defined in a certain way, and there's another space that defines another family of distributions where the potential are changing in another way. And the difference between these two spaces is that there is one difference, okay, in the potential function that you have to make it different. And then this projection is basically getting you the optimum change between the two families. And the way to attain that projection is through maximum entropy, as you can show in the next story. So what is happening just now is, can be understood, using, another KL divergence argument, which we're going to use a lot in our future study of, say, variational inference and other deep learning techniques. So I'm going to use the story, introduce a story here a little bit earlier. So the general problem, again, that's another way to frame the maximum likelihood problem. Originally, just to go back to this equation where it comes from, right? It is from a maximum likelihood argument, right? And I argue that the same conclusion can also be derived from a equivalent but very different argument, which is known as the KL divergence minimization. Okay, so we have an empirical distribution, and we have an estimated distribution, and I want to estimate the parameters in this distribution such that their KL divergence is minimized. Okay, that's another preferred way in the information theory community to estimate the model. And very often that they give you the same results as maximum likelihood. So here is how it worked. You know what is a KL divergence? Okay, so if you don't, let's cover that maybe in recitation or offline. And that's basically a way to measure the discrepancy between two distributions, and you want them to be as minimal as possible to qualify a learned distribution. And suppose that we are going to break the arguments in the distribution into two parts. One is xc, the other is xc complement. And the purpose here is to carve out a particular potential clique. Okay? And there is a chain rule that you can use to break also the KL into a slightly more complicated expression, which basically focus on only the KL between parts, and the other is a KL between the rest conditioning on that parts, and then averaged over the marginal of that parts. Okay. Again, if you just digest what I just said verbally, it cannot make intuitive sense. Parts, something else given the parts, averaged over the distribution over parts. So it looks like the whole story, not losing anything. Okay, that's it. And then our goal is to basically find this potential C. And you can show that they are not going to affect this part. Because in these distributions, this potential is not going to play a role. Okay. So at the end of the day, this one is going to only affect this particular term. Therefore, to get an optimal value of the phi c, you only need to minimize this part of KL, which is the marginal between Q, the marginal of the clique, and versus the empirical of the clique. So that gives you basically the same identity as we had before, which is xc equals to p of. Okay, that goes back to the same identity function that we said before, and that gives you still an opportunity to define the fixed point iteration. Okay, so that's all for IPF. Very, very trivial. Any question with that? Basically, all you need to do is to now start from somewhere, a random guess of the potential numbers. And then each time you are going to multiply it with a ratio, which also kind of makes sense. You're getting closer, to the ratio of the empirical versus the estimated marginal, and you're adjusting it. That's why it's called iterative proportional fitting. Okay, and until you basically can go no further.
Do we have convexity in respect to the times?
We don't have a convexity guarantee here, just like in EM algorithm.
I can review it offline, but in the earlier slides, for example, we were taking the derivative of second equal to 0 and assuming that was a minimum, right? And
What's that?
A lot of this is based on, not necessarily these slides, but earlier on, it was based on the idea that if we found a critical point, it was a minimum and a global minimum. Right?
The only issue here is whether you have a global or a local. It's not about, convexity is not an argument for disproving, a algorithm. It's really for qualifying whether the algorithm leads to global or local optimum, right? So that's it. And as a reminder, what if you have a non-convex function? That's just part of life. And then what do you do? In the simplest case, with this typical algorithm, which guarantees you only local convergence, what do you do then?
Do we have at the very least that it has a critical point?
Let's get intuitive. We're computer scientists, right? Yeah. You want to do something affordable, truly affordable and robust. And we learned that from EM already. What do you do? Come on. Yeah, you use your random number generator and initialize 100 times. And estimate 100 times and pick the best one. That's it. Right. So that's basically where real soldier versus bookroom soldier are different. The real soldiers, when they are in the battlefield, they will fight. Okay, they will do whatever. And I have to share with you that in my past experience in here, I even ran into fourth-year machine learning PhD student don't know how to run a k-means algorithm. Okay, because they ran it only once. And then that's the result. And those students, I wouldn't want you to identify because they already are not here. They could write papers at NIPS and Annals and other places. So that's a problem I want to avoid, at least in this class. You want to actually know the theory, but also you want to get it work. And even if the theory isn't guarantee you ideal results, you want to then get the sub-ideal results. There are some results out of it. Okay, so in this case, yes, this algorithm, that's why I call it a workhorse algorithm. And sometimes it gets you what you want. And if not, then just unleash the workhorse and let them run and get you something. At least there are some good things out of it. Okay. All right. So so much for the first algorithm. The second algorithm is way more interesting. So let's start turning to that. I want you to start now thinking more about the models now. Okay. In particular, feature-based models. So this potential function is a mysterious thing. So far, whenever we mention potential functions, we always feel, well, it's trivial. It's a bunch of numbers, right? And either I learn it, or I just at will specify those numbers, and then that's it. But there are some problems. For example, let's talk about a real task. Again, being real is very, very important. It really opens up your mind. Let's talk about a very, very small problem on spelling checking. Okay, not even natural language processing, just spelling checking. Okay, not even context, semantics, everything. And one of the very, very useful, powerful device in spelling checking algorithm is to really built on affinity models of strings, character strings. For example, let's talk about maybe the consecutive appearance of 3 strings. Okay, and the rationale is that if we can use this to score the likelihood of misspelling. For example, if you see a string of ZYZ, do you think it is a correct spelling? Did you see ZYZ in your life in part of any word? Okay. Sure. So what about INK? INK, right? So let me give you 2 things. These are 3 characters, right? So basically, that's how a triplet of potentials or whatever likeness can help you to even do spelling checking already, right? Okay, so then maybe it looks like the idea is that let's call this a potential function over a triplet of characters. Then what are you going to do? You are going to do 26 to the power of 3 different features, and then put a function on that. How about 5? 5 characters, right? So that basically tells you a need now already on feature-based models. Basically, what I just gave you is an example of those infeasibility of the so-called tabular potential. The tabular potential are for very, very trivial problems that you can tabularize it. For real-world problem, just like spelling checking, there are many other things where every variable has a bigger space than 26 characters. You are going to actually exhaust your computer memory to even store, a table of potentials. Okay, then what's the way out? I have my next page, but I want you to do a guess. What could be a smarter way of doing it?
You could, instead of defining a unique table for each potential function, define the basis of tables that are, right, and have the coordinate or the amount that each basis table contributes based on features.
I had a hard time to understand it. Maybe possible, but I'm looking for something even more dumb, more intuitive. Okay, I'm not going to tease you anymore. So, how about do this? We as English speaker knows basically how often those and how those what are those frequent triplets, just by exhaustively check dictionary or just based on our own vocabulary. For example, ing, 8, and ion, or maybe anything plus ed, and qu after anything. Basically some are more frequent, some are infrequent, and some are probably even impossible that you don't even care to look at them, right? How about we just instead of coming up with this 26 to the power of 3 minus 1 parameters, we just first pick out those special citizens that we really, really feel very sure that they are very likely to be correct spelling, or they are very frequent in our English vocabulary, and give them a feature. For example, I would say f of ing to have a score of some number, maybe 10. Okay, and maybe f of 8 has about 9, whatever. Okay, I bet you are going to be very tired after you enumerate 20 of that, right? And you may have a second tier where, say, this and this may also are believable. Okay, then you have a second tier. And then at some point, after you are about reaching 50 or 100, I bet you are tired. You say, okay, I don't care about the rest. They should all bear the same feature. Basically everything else, question, but not here, we'll get some arbitrary number, say in alpha. Okay. So this is the handcrafted feature design. It's a very important art in machine learning. And you can see how human intelligence, how human knowledge plays an important role in designing, an AI agent, in helping, very specific applications. And the result, of course, is a huge saving, okay, of the representation cost, and as a result, the computational cost, and as a result, better accuracy. Okay. So these are known as a feature-based model. This is very, very different from the current trend of deep learning, where you have a vast placeholder of everything. You become overcomplete, okay? And then you hope that the big data is going to funnel in and try to get all these numbers in their place and so forth, with no guarantee, because we don't actually know how much number is needed to get those numbers in place. We don't actually know the sample complexity. But in here, human knowledge are actually actively introduced. Right. So in the past, I have always had a question or maybe a disagreement with certain school of machine learners who proudly claim that, hey, I've got a great algorithm. I need no human involvement and no human input to achieve so on and so forth. I ask, why you do this? The entire history of human civilization is not useful, and you rather pretend them not exist and find something from the scratch. What's the point? Rather than prove that you are smart. Right? So here basically is a very different school that we actively seek the best possible way of utilizing even intuitive common sense human knowledge to build a model that is working. And the feature-based model actually is very popular used. In fact, now, if you can look at now, the most successful speech recognition models and any other models, actually they have the foundation still based on this. And it looks like this. You are going to now have a finite number of K features, which are defined over the space, say, of 3 characters. It could be other numbers as well. Okay, and these feature weights can be handcrafted because you have your human knowledge. You don't know how important this feature can be in this particular context or in this data set. Therefore, you leave a weight that is unknown. Okay, and then your overall potential function is exponential sum of these weighted features. And that defines a potential function. Okay, so this potential function is called the feature-based function. It's also known as the micro-potentials, each of them. Okay, it's very different from the tabular potential we talked about before. Okay, it's a lot less complex, a lot more compact. Okay, and also capture very precious human intuitive and prior knowledges. Then, of course, there's no free lunch. Okay, by the way, these are how you combine if you have multiple such cliques. I just talked about one clique with 3 characters. And if you do spelling checking, you may want to, basically do sliding window, right, over all possible triplets. Or you want to do partially overlapping sliding window and having, triplets and pairs and other quadruples and so forth. And then you can basically have this cocktail of features. But it doesn't change anything, in terms of the anatomy of the model. Okay, so you are going to get again, a weighted sum of the features, and at the end of the day, you are going to get a model like this. And if you recall this, okay, maybe you don't recall because we neglect that particular part. It's one family of the generalized linear models. Again, as I said, there is no free lunch. You get compactness, prior knowledge, and a lot of other good things by this redesign or redefinition of the potential functions. But you could also already expect that the complexity or the difficulty of the learning is going to be harder, because otherwise it's too good to be true. It's not like real life, right? For example, in this equation, the IPF, all we know is that this entire thing can be reweighted, okay, iteratively. But this entire thing now becomes a a combination of theta and f. Okay, and how to decouple these two? One is designed, one is estimated. It's not very clear. So there isn't actually a clear path out using this technique. Okay, IPF doesn't work for feature-based models. Okay, so with that, let's take no stop and continue on the new mathematical algebraic effort to hopefully tackle this problem. Okay, so here, let's first of all look at our new loss function. So this is our new loss function. Well, I introduced a term called scale likelihood just to allow me to introduce a empirical distribution, but that's a technicality you can put aside. So my now scaled, because n is a constant, therefore it doesn't change really the relative numbers of my estimate. So my loss function now is this term. Okay, and it breaks down into two terms. One is a very innocent sum of the weighted features, and we see the theta here already. The other is a little bit irritating, right? It is not only z, but the log of z. Basically, the theta is buried deeply into a compound manipulation. So you can imagine that taking derivatives and setting zeros and so forth is not going to get you anything. You can try it. People tried it, didn't work. Okay, so how to start gradually simplify it? So here are some rationales that you can use. When you see something that is nonlinear, usually the difficulty are really caused by nonlinearity. The nonlinearity could be a logarithm, could be a inversion or whatever. So you're going to try to linearize it, right? So that the argument hopefully can be exposed out as a linear term. Then when you take derivative, it's going to establish equality very easily, right? So that's kind of a mathematical intuition you want to have. Very, very generically, it's not even for this particular problem, right? That's the way to get a solution out. So let's look at this nonlinear function. And if you still remember some college level calculus, you know that this logarithm is upper bounded by a tangent of arbitrary slope, right? And this is the expression of that tangent. And the nice thing here is that, okay, so log is gone. Basically, these two things becomes a linear, right? And also, it is true for any slope. Therefore, I can choose a slope to be of this particular thing, which again used this trick of a fixed point iteration idea. I'm already assumed that it's not going to be a closed form equation anyway, so I'm going to start from somewhere and estimate the next step iteratively. So I assume that there is a previous version of the theta exist. So I'm going to basically define a inverse of z that is calculated from the current version of the parameters. Okay, so putting things back, I got this. So okay, let's see, what do we get? We still have our argument in here, and we have our argument within this one. Okay, at least better than before, right? It's not a log of z, it's only z. And then just again to make my task even more explicit, let's establish a explicit relationship between the desired estimation of the theta versus the current version of the theta, and let's call it a delta. Okay, I just want to this is just an identity introduction to kind of expose where my question is, and I'm going to basically copy the term here, and then introduce this particular thing, into what we have here. Okay, so here, I think again I'm not going to check all these equations here. this particular theta now is replaced by this guy and that guy. See that? And what else? Anyway, it must be correct. I checked when I was having a clear mind. Okay, so still quite difficult. Why? Do you know? Here you already see something very nasty. You are computing, the delta. That's really your goal, right? But this delta is now compounded by a summation of all the delta over all parameters, and then exponentiated. It becomes nonlinear, and they are coupled. Basically, every delta is now coupled with every other delta because of this iteration operation. Right? So this additional layer of nonlinearity is no good. Okay, but you also notice that this particular thing is taking a particular form. It's an exponential of a sum, or weighted sum of something. If you still remember, I don't know, Morion covered EM algorithm to the level of detail that there was a particular moment where we used a trick to turn, to use a convexity bound basically to really turn a exponential of sum into something else. Yeah, Jensen's inequality, right? So which I wrote here. If you want to take assumption that say this again, so here you have a symbolic change. Okay, we often say that f are the features and theta are the weights. Yes, that's for sure, because that's semantically the rationale behind our design. But algebraically or numerically, the computer doesn't care which is called feature, which is called weight, and so forth, right? So in this case, let's do a twist. Let's treat mathematically the f's to be the weights and this one to be the arguments. Okay, then if we can assume that all these weights have this convexity constraint, okay, that they are all positive and sum to 1, then we can use Jensen's inequality to relax this into a upper bound. And then suddenly you have this new term where you have now a sum of exponentials of every individual delta rather than the exponential of the sum. Okay, so these two steps of relaxation is now liberating basically a heavily embedded argument that you want to solve to something that is only linearly coupled with others and can be easily solved in a closed form operation. Okay, so this is a algebraic trick that machine learning people often use to derive some algorithmic operations. So this algorithm is known as GIS because after what I did already, you can do some quick additional manipulations. So instead of using the original scaled log likelihood, you use the lower bound of that, which we call the lambda, and you take a derivative of every parameters, set them to 0. At the end of the day, you get an update function of the theta of the delta theta. In here, I wrote it in exponential form, but it's the same, right? You can just do one more step manipulation if you need to. Okay, so and then of course, once you get everyone like this, you can combine together and get the whole distribution to be look like this. So this is called the generalized iterative scaling, and it is iterative. It is also a scaling. Why? That's the reason. Excuse me. Take a look of this last equation. It is in the form of a ratio, right? Calculated over two methods. One is the feature weighted by its empirical probability. And the downstairs, you have a feature weighted by or averaged by the inferred probability. And you have, if you remember the IPF, same kind of flavor. It's a ratio between what you observe and what you estimate based on what you have now. And then you are going to, in this case, lift it, exponentially by Fi, but that's a algebraic treatment, and you basically are, refitting or rescaling it, iteratively like this. And again, compared to the IPF, you can see there's some kind of conceptual connections between these two ideas. Okay, so I want to still spend some time to talk about other important topics. So I'm going to wrap up here on the algebraic details of the two algorithms. So in fact, both of them are fixed point iterations. So take home message, fixed point iteration based on a log likelihood based objective. And secondly, one is for the tabular potential, the other is for feature-based potential. And also, hopefully, you now appreciate the kind of the interest and the needs for those feature-based models in many practical application domains. Any other questions before I move on to some more fundamental discussions on what we actually are doing right now, with all these different models? Is there a unified theme between it? Questions? Are you all with me still? Thank you very much. Because I know it is a little bit confusing. In the past, I wasn't able to go it very well, but today looks like you guys are really, really working hard to catch up. Great. So you probably notice something that is already coming into a pattern that either by choice or by design or just by a natural consequence, we seem to be often run into this term called exponential distributions. Right, so here is one example, how exponential distribution can come from. So we have this maximum likelihood estimation of exponential functions. Right, we, say this is our general form of the exponential functions, and then we basically come to a property that once you follow a very, very standard maximum likelihood estimation principle, you found that this type of distribution, exponential family distribution, gives you the following property where the expected feature weights or features is equivalent by the empirical weighted features. Empirical basically means that the distribution is really computed from data. Okay, so what it means that under ML, the expectation of the sufficient statistics under the model must match the empirical feature average, right? So which kind of makes sense. And then this is by beginning from a maximum, from an exponential family distribution assumption, and then what we have here is actually, a consequence. Okay, we can actually also seek to reverse the rationale. How about treat it as a given? We're going to say that I want to just estimate any model, such that I want this model to be rational. What do I mean by rational? I mean that under this model, the expectation of a feature must match my sample average, or some other facts that I can get from data, which denoted by alpha. So basically, I'm constraining the distribution so that you cannot give me arbitrary distributions. And I'm going to use a new technique to make the estimation, which is known as a maximum entropy estimation. Basically, find a distribution, and there are many distributions in the world, and I want two things. First, the distribution as a result, when I use it, has to match my constraints, okay, defined by data. Also, it has to be a proper distribution. It has to normalize to itself. And then, other than satisfying all this, I want the distribution to make least assumption about the world. Okay, in the world of information theory, if you, in fact, unfortunately, I don't know, we don't have an information theoretic class now in MLD. Hopefully, we can open it. But Shannon basic states that you can use entropy to measure the amount of randomness or the amount of assumptions you made, using a distribution. So we're going to maximize the entropy, okay, given that these conditions are satisfied. And that's another way of estimating a distribution. It's known as a variational principle. You define a distribution as a solution to a constraint optimization problem, okay? And how do we do that? Just to review, if you've been in 701, if you touched the SVM, you probably know the general technique. What? Using a Lagrangian approach, right? Yes, we define a grand Lagrangian, right, which contains the objective and the Lagrangian multipliers, over all the constraints. Okay, this is the grand Lagrangian, and then we take a derivative of the grand Lagrangian to all the folks that you want to estimate over. Okay, and then you set them to 0 and so forth. And it turns out that at the end of the day, the natural consequence of this approach gets you a distribution that takes this form. Okay, it looks exactly as an exponential family distribution. So in here, the rationale was reversed. We start from the consequence that we want to achieve, and we ask to get a distribution from any family, okay, with a least assumption, and then turns out that those distribution has to be in the exponential family form. So that's why, very often in machine learning, this word exponential family distribution are so often used without even making an assumption, because it's a natural consequence of many good intention and good effects. Okay, so in fact, if you have a prior knowledge, I just said that I want to absolutely make a least assumption about the word. But what if you do have some assumptions and you want to make least extra assumptions of that? Okay, and that's actually now making also the Bayesians happy. By the way, as of now, I have mentioned nothing about Bayesian because there isn't a need for Bayesian principle. But if you really, really want to reconcile the Bayesian with what we do so far, you can still do that. Let's assume there's a prior distribution of X. Therefore, you want to make a reference of that so that my estimate distribution has least kind of additional assumptions from that. Then you can define a KL between these two rather than just using the maximum, the entropy argument. And then at the end of the day, you basically still get a exponential family distribution where this prior H appeared in here. Okay, they get multiplied by these additional new components from data, and then everything will be normalized together to form a proper distribution. Right. So kind of very magical, from maximum likelihood estimation, from a maximum entropy estimation, and a number of other principles, exponential family distribution gives you almost like a convergence. So what we just see in the second approach is known as constraint from data. It's also known as the methods of moments, in frequency statistics. And arguably, it is also a very clean rationale behind, model estimation principle. Because if you want to make no assumption, but at least you need to agree with your data. Otherwise, you shouldn't even work on the problem, right? So here we want to basically make the data itself as the constraint, okay, rather than as a driver. So here maybe there are some philosophical thing. Sometimes people may say maximum likelihood may not be that appealing because why I have to say that my data has the biggest likelihood? What if I pick the wrong data and so forth? Okay, fine. Don't argue about that. How about your data, your estimated model has to respect your data to at least give you the right correspondence. And here you actually could use this argument to sustain that desire. So to quickly wrap up, I want to summarize by just giving you maybe a more holistic view about all these different estimation principles and the styles, in the world of graphical models, right? One is to begin from assuming a model family, say an exponential family distribution. We start from a scripted E with all this, form as a placeholder and not knowing, say, the theta and so forth, and I'm going to estimate. The other is I'm going to take no assumption of the distribution, and I just want to define a constrained space, okay? And I want them to satisfy certain data constraints. And interestingly, there is another Pythagorean-like theorem, in the information geometry, which can be expressed like this. Okay, this is not the general geometry Pythagorean, but the information geometry Pythagorean. And you actually could easily, equivalent the two estimation approaches and prove this identity, which I'm not going to spend too much time on. Okay, in fact, if you just look at the thing here, you will quickly recognize that in the estimation problem itself, either by minimizing the entropy or minimizing the KL between the empirical and the estimation, the two terms in the Pythagorean, only one of them is playing a role. The other term is actually not even affected, which actually makes your estimation principle rather straightforward. Okay, so that's where I want to close. The take-home message is for this particular part should be that you have now hopefully come to a realization that the exponential family distribution can be viewed as the solution of a variational expression, and we're going to use the variational principle heavily, in the rest of the lecture to inspire approximate inference and also to inspire deep generative models and many of the new modern literatures, which unfortunately fail to very often acknowledge the root of where those ideas come from. But I'm going to make those explicit, and you actually could see that some of the work could be easily understood and already established a decade ago, or maybe 3 decades ago already. With that, I have 10 minutes. I do still have some time. Let's do, again, maybe next class is about causal inference. I intentionally skipped an important topic called structure learning, how to learn the graph topology in graphic models from all the lectures. You may find a few algorithms already in the supplemental materials, say in learning observed models. You can already take a look. I believe the guest lecture will cover one or a few of these algorithms. So I'm not going to say too much about that. I want to return to this old subject about the art of modeling and tell you again, how a experienced modeler make decisions and judgments when they run into a real-world problems, and then justify the model. In fact, I hope I still have 10 minutes should be enough. I'm going to just expose the problem, but the rest of the reading is for you to just enjoy how that model is solved. So anybody know about the word conditional random field? We mentioned about it, but have you heard it elsewhere from other than the class? Do you know where it is invented? It is very proudly very here. Okay, it was by one of my most respected colleague, John Lafferty, who is unfortunately now in a different school. It was invented when I was a grad student, and when it was invented, I was just about starting my own study of graphic models, and I remember, the Michael Jordan group received the preprints of this paper. We were so excited. We spent a week even trying to understand what this paper was talking about. It was very, very complicated at that time, we thought. And we were actually quite impressed by the way that paper was presented. And you can look at the old-fashioned way of writing papers in terms of the clear rationale and also the motivation behind the thing, and then all the beautiful math coming after. So here is a problem. It comes from again, every new invention usually comes out of a shortcoming of an existing approach, being inadequate. And we know that in HMM there are a few inadequacies already, right? For example, in HMM, you basically at least can see the following limitations. This state only corresponds to this observation. Therefore, every hidden state has limited influences on the observations. It's very local, right? And sometimes, when you are assuming this as a sentence, what you appear in here may depend on the whole page, or at least the whole line. If the whole line is bold-faced, has a bracket somewhere, in fact, it could influence the content in here. But in HMM, this is impossible to model. Okay, and then there is also another very interesting thing. There's a mismatch between the learning objective and the inference objective. When we want to learn this, what's the purpose of HMM? The purpose of HMM is to really, at the end of the day, be able to allow you to do this, right? And but when we learn HMM, what do we actually do? We actually are maximizing the joint probability of X and Y when everything is observed. If only the observation is observed, then that's even a less relevant objective. So you are basically, you want to go to New York. Instead of going there directly, you go to Philadelphia first, and then go north next. That's kind of the way it is achieving here, right? All right. Then there is another problem. I just want to state it, and then we're going to close the class, leave you go home and hopefully appreciate it. It's called a labeling bias problem. It's very hard to explain to people. Let me give it a try. Okay. If you look at the original paper, the rib and the rob example, I highly encourage you to read it. It's still very confusing and confounding. So let's look at a model like this. Okay, with 5 hidden states, and let's say it's transitioning into 4 steps. Okay, and the first state somehow, for whatever reason, has 2 outgoing states. It has a probability of going to itself at 0.5, 0.4, and elsewhere 0.6. And then the next time it is going to have a slightly different probability. And here we assume actually non-stationarity. Okay, but the number of states it can go out is only 2. Clear? The second state has 5 different states to go out, okay, which are numbered in here with a mass, on each of the edges, and so forth. Okay, so that's basically a model. Okay, so now let's look at a rough estimate observation about this model. Okay, basically, if you look at the model, it looks like state 1 always prefer to go to state 2, right? Because every time when there is a branch, it has a bigger mass to go to 2, right? And then state 2, it always has a probability, a higher chance to stay in state 2 compared to elsewhere that it goes, okay? And that's basically the high-level messages we have from this model. Now let's score all possible paths and see in practice, okay, in this model, what is most likely. Okay, let's see this path, 1, 1, 1, 1. And you just calculate the joint probability is going to be 0.09. And how about another state sequence, 2, 2, 2, 2? Okay, 0.018, much smaller. Okay, and another thing, this one, 1, 2, 1, 2, that kind of state transition, it has 0.06. Okay, and maybe another thing, 1, 1, 2, 2. What's the probability? 6. Okay. So did you find something odd in here? Something a little bit counterintuitive? The model says that when I'm in 1, I prefer to go to 2. When I'm in 2, I want to stay in 2. But in all my 4 sequences, when I'm given this chance, I never are able to substantiate or justify it just by stacking all the numbers together. Right? The number somehow isn't honest to me. It's kind of deceiving me that I still basically get the 1, 1, 1, 1 to be the most probable sequences. So if I'm designing a model that is going to run a machine where I want to achieve such an effect, the actual operational machine is going to give me something else that I don't expect to happen. That's basically what something called a labeling bias. This bias actually is due to what? You know what? It's actually because the mass of state 2, even though relatively it is still more likely to stay in state 2, but it has a 5 outcome. Therefore, the mass gets spread out too thin. Okay, it's because of this locality issue that makes it less competitive to the first one, even though all my design rationale is the same. So this local normalizability is it's a double-edged sword. It makes the computing very simple because local normalizability means that every time in this local set of all possibility outcomes, they sum to 1. That's the local normalizability. HMM is like this. If you define all conditional distribution in a directed model, then every local conditional has to be normalized, right? But what you want is actually a global, much more contextualized effect where you want to achieve the high-level effects like staying past 2 or switching from 1 to 2 and so forth. So how we do that? What's the better way? Alternatively, achieving the same effect without changing the technique, right? So here is the alternative approach. Instead of putting them to be normalized numbers, I'm just going to put scores like this. These scores are roughly the same as what we had before. Okay, but now they fail to normalize each other. And especially on this one, you can see that they have this, again, the spread, allowing them to go to all different places. But their strengths now become comparable to the strengths of the outgoing action from state 1. What do you lose by doing this? It fails to become probability because all these numbers does not sum to 1, right? Okay. Then John Lafferty said, okay, I don't care about the local normalizability anymore. Let's make it a random field. Okay. Basically, call this the feature, x, I, and j, and give them a weight, and make the whole model, the sum of the theta I and the fi and exponentiate. Okay, so that's basically where the conditional random field comes from. And then, of course, in these features, which correspond to the little numbers in here, you basically have, again, the human prior knowledge to guide you, just like what we did in spelling checking example, to insert the numbers of these features. And then the weights can be decided by the real examples. So there are, much of the paper was also about inference and learning algorithms, which I don't have time to cover. But again, it's a kind of a good tribute to the art of modeling. Happened in the good old days that people are taking too much thought, by designing a transparent, totally comprehensible model, that captures human knowledge and does good work, in practice. All right, thank you very much. I will see you. Okay, someone else will see you next week. Yeah, thank you.